So our next speaker is Sascha Gehrmann, who will speak about quantum SL2 invariant staggered six-vertex model.
So yeah, thank you very much, and also let me thank the organizers for organizing this awesome workshop and having me here. And yeah, so how do I do the pointer?
Click on the window. On the computer. Click on the window. With the mouse. Click. Bring it to the photo.
Sorry.
And point it to the computer.
Now it should work, right?
So is it this one?
So this is the light, but these are the arrows.
Yeah, but I don't see any light.
But maybe just turn it off.
Oh yeah, that would be great. Yeah, sorry. So this talk is based on a work with my supervisor Holger Frahm, and we are in Hanover. And yeah, regarding like the triplet of topics we have in this workshop, I would consider like the most fitting ones are the later ones. And yeah, let's just jump right in. So the inhomogeneous six-vertex model was introduced a long time ago by Baxter. And interestingly, due to this most very various inhomogeneities you can put at each side, you have like a multi-parameter model, and then you can try to basically tune these parameters to explore different universality classes. And actually one interesting phenomena was observed in recent years, and this is actually the emergence of non-compact degrees of freedom from compact ones. So when you have like a normal spin chain, you would expect that you have at each side, you have like a compact degree of freedom. And when you have like an effective field theory describing this energy regime, you would expect that like the target space of these fields describing this model is still compact. However, these studies show that this is does not have to be the case, and to actually explore this phenomena in the staggered in the vertex model, six-vertex model, specific choice of the inhomogeneities is needed. Actually, staggering, and staggering means that you have like the inhomogeneities, and you basically repeat them periodically in some manner. And we will do that here for the Z2 staggering, which means we have on the even sides the one inhomogeneity, and on the odd sides the negative one. So this was done for the periodic case. It was studied, and here you see like the field theories describing the low energy regime. So it's like given here by a compact free boson. So this is all compact. This pink region was studied by Kutuzov and Lukyanov by studying generalized Afin-Godard models, and then it. Sorry, on the axis it's like the inhomogeneity, so which like is on the even sides and minus on the odd sides. So this is like then the parameter. I will introduce like the formal thing just in a couple of slides, and this is the anisotropy, right? And there you have like also like a compact field theory. It is given by two Majorana fermions and one compact boson. And in this region, since I have told you I will speak about non-compact degrees of freedom, this is the black hole region, which means that the scaling dimension has like a continuous component, and this is non-compact. So this is a periodic case, and then the question is what happens when you go to the open boundary condition, and there relative little is known. Also just this small line was actually known, and the topic is like to explore this parameter space for the open model. So like a quick overview, we will recall quickly open boundary conditions in staggered models to formally introduce all the notation, and then we will study at the root density approach, and then at the heart lies the finite size spectrum analysis. And we will end with summary and open problems, of course. So the ingredients are fairly simple for this model. It's like the standard XXZ R matrix here in the symmetric gauge. And yeah, just note like the standard properties that you have like at the spectral parameter U to 0, you have like the proportionality to the permutation operator, you have unitarity and all this stuff. And besides the R matrix, we have also fairly simple K matrices. So remember, just for the next of the talk, that actually this R matrix is just e to the spectral parameter and then sigma z. So, and as you know, you can basically construct periodic models by just taking the trace of the auxiliary space. For the open case, you have to insert these K matrices here and then take the trace over it. And when you have like these reflection or boundary Young-Baxter algebras, when the K matrices and the R matrices obey them, you can also construct yeah, a family of commuting operators. So one thing to mention here, in the open case, you have normally not as a Hamiltonian limit like the logarithmic derivative, but you have like the simple first derivative, and A and B are some constants. So this is for the open boundary, and let's introduce staggered models. So you can do the same integrable construction. You don't spoil integrability when you introduce some inhomogeneities. This was like the multi-parameter space which I'm talking about. However, we will restrict here to simply to a very small subspace, which means that we have alternating staggering. So we have here on the even sides, we have like a plus I alpha 2, and on the odd sides, minus. And yes, so this was then in the horizontal direction. We will do that the same in the vertical direction by multiplying two of these transfer matrices together with a shift in the spectral argument. And when we do that and use graphical notation, we can represent it as this object. Here, the vertices are just the normal R matrix, and these like arrows with the kink, it's basically then the K matrices. And you observe here like that the staggering in the vertical direction as well in the horizontal direction. And to get a local sorry?
You have already, in a single double row, you have U minus IA, U minus IA, U.
Yes.
It looks like a checkerboard. Why do you need to stagger it more?
Okay, it's, but the double row is just for the open model, right? You have always like a double row for open models. So this is like a natural thing. It's always like, this is for the open models, you have always that in the later R matrices, it's like the negative one. So this is not a real staggering. It's like always just to have integrability, you need that. So this is not a real staggering.
Because the arrow is on the other side.
Yeah, exactly.
Okay.
Yeah,
okay.
You have like here and there. Okay, to have like an local Hamiltonian, we would like to have like that this object is proportional to the identity operator, and this is easily fairly checked when you just note that the R matrix at 0 is a permutation operator, since then we have like the arrows go to that, right? And then it's very nice that you have like here then the unitarity condition, then you can pull this line there, and this line there, and this line there. And then another unitarity condition is popping up, and then you can have like in the bulk the identity, and then remember the specific form of the K matrices, e to the u sigma z, they have like negative arguments, so this is also the identity. However, I hope I have provided enough evidence that you believe me when you like evaluate this loop diagram. You have also like the identity, but I won't go into detail that. So we have like a transfer matrix with this identity at spectral parameter equal to 0. So when we take the first derivative of this object, we can get a local Hamiltonian, and this is in its full glory. So it's indeed local, since this maximal interaction is like 3 sides. And there's a couple of things to note here. First of all, it's actually not not Hermitian. Since we have like here these complex magnetic fields on the first and the last sides due to this I here, and also like the 3-point interactions are not self-adjoint, since basically due to this one minus here, so these are swapped and they get a minus back. Yes, I'm coming. Yes, exactly.
Yeah, I have another question regarding this Hamiltonian, because as you said, it's not Hermitian when you're, I mean, considering gamma to be real, I guess. But there's this beautiful result by Robert and maybe also Christian Kolff that for the homogeneous case, even though it's not a Hermitian, the spectrum is still real.
Yes,
It is pseudo-Hermitian, right? So is it the case here as well?
No, it's not the case. So for, I will say, so the spectrum of this Hamiltonian, the low energy spectrum, this will be real, and I'm just interested in that since I will just focus on the effective field theory describing the low energy spectrum. And these eigenvalues are real.
But the full spectrum...
The full spectrum is not
real.
complex,
okay.
Yeah, it's complex.
But then how do you know this is kind of a low energy in the sense that since the eigenvalues are complex?
Just the real part, yeah. The real part is... So
you only consider a sub okay, of the spectrum. Okay, thank you.
Yeah. So one can then first study what happens when we go some limiting procedure. So first of all, it's clear like when we send the staggering to 0, then we get like the normal homogeneous open boundary XXX Hamiltonian back, since the only things which survive is like this and this part. So now one interesting thing happens when we send the anisotropy to 0. Since we get, okay, what we expect is then XXX, but what we get is not the open boundary, we get the periodic boundary one back. And this is easily understood when we look at these terms. This is the only term which survives here in the bulk. This goes to 0, this goes to 0, this goes to 0. But these three terms also stay. And you have like this term, and this is like XXX, but it couples only even sides to even sides and odd sides to odd sides. So you have like 2 copies of them, and the boundary terms, the original boundary terms from the matrix, then these are coupling odd and even terms at the end, and then you have like a periodic chain. So this is nice, and then we can, first draw some lines in our phase diagram. So homogeneous, and oh yeah, I should also mention this is a ferromagnetic one, right? Ferromagnetic XXX. This is a new phenomenon popping up. So, and also for the questions already, this Hamiltonian has a specific symmetry. It has UQSL2 symmetry in this representation. It was shown a long time ago by Kulisch and Sklianin. And yes, this will lead to some interesting features regarding its ground state, since we have like a full algebra, so we have like a spontaneous symmetry breaking, since the ground state has the same energy for all these value of this UQSL2 spin. Besides this symmetry, it has also like a duality symmetry regarding like this spectral parameter, the staggering parameter alpha. When we send this to pi minus alpha, the transformed transfer matrix becomes similar to itself, so its spectrum stays the same. And with this transformation, we can basically swap in this phase diagram around, and hence we have just to study actually one side of the phase diagram, since we get the other one by the duality transformation. So, and to get like into the interior, we have to basically now go into the techniques. So we use like the Bethe ansatz, which was developed by Kulisch and Sklianin a long time ago, and these are basically then the whole Bethe equations and the eigenvalues of the single transfer matrix. And when you then multiply these the eigenvalues together with the shifted arguments and then take the first derivative, you basically get then that the energies has a fairly simple expression in terms of the Bethe roots. And also like these energies are invariant under this transformation, which is mirroring this duality transformation of on the level of the Hamiltonian limit. Yes, exactly. Yeah, and now I have to introduce something out of the blue. Besides, like as Jules had already said, like the Hamiltonian is obtained like the first derivative from the product of two transfer matrices. You can also like go and study other quantities which are conserved. For example, like the quotient of both, and this is then the quasi momentum operator. You can also express them in terms of the Bethe roots, and this is like, I'm sorry, out of the blue, but it's actually a very crucial object to identify the CFT which is underlying this model. And in the graphical notation, this is basically, yeah, this operator with a checked R matrix here in this rotated geometry. So to restrict ourselves to the low energy regime, what we have done, we have studied like this Hamiltonian we have implemented, and then just also simultaneously solved the Bethe equation and have seen that this configuration of Bethe roots are describing the low energy regime, and when one has identified that, one can also show that they are condensate on the whole line, so they're getting more and more and more, and they are also filling the whole line. Then one can basically derive linear integral equations to study these the root densities, and these are of these kinds, and this is for the ground state. And since the integral boundaries are infinite, one can basically solve this easily by Fourier transform. I haven't given here the driving terms, but yeah, I'm just stating like the results, the solutions. These are given right here. This is the same as one expect for the periodic model. However, we get a different, which is non-present in the periodic case, the surface contribution. Yeah.
I mean, there should be bound state as well, right?
Yes.
Do they contribute, and why? I mean, since you're saying the spectrum might be complex, so is it still true that the bound
state? For the low energy regime, so when you plug in this Bethe root configuration, these are real.
Sorry?
The Bethe, when you plug in these Bethe roots configuration in the energies, you always get real energies.
Okay, that part is fine, but shouldn't you consider Bethe the bound state? That doesn't they contribute to the low energy spectrum? I mean, bound state as in like Bethe strains, if you wish.
Yeah, we have. Yeah, the bound states is a different topic. I have put them out of here, since you can also. Do you mean like bound states like with strings?
Yeah.
Okay, no, we haven't found any of them.
But this is about the ground state.
Yeah, this is just the ground state, right?
The ground state now.
This is not. Yeah.
Okay.
Yeah.
So okay, thank you.
Okay, so these are the densities, and one interesting thing is basically that they become the same, which mirrors the self-duality on this line for this staggering parameter, and they are vanishing here easily. One can see at this, and also vanishes at this staggering parameter. Which means that we can basically say that there's at this line where the density vanishes for the ground state happens some phase transition, and for the rest of the study I will restrict to this interior, since the other ones we haven't studied yet. So, but this looks fairly similar as the periodic case already with this triangular thing. So when one has like the densities of the ground state, the bulk and the surface contribution, one can calculate the predicted spin of the ground state, and one should check that when we go to the when we send gamma to 0, we was obtaining like the ferromagnetic periodic XXX chain, and we should check if our density approach is recovering with the result, and indeed it does. When one integrates like the densities, one can calculate the number of Bethe roots, and then one can calculate the UQSL2 spin of the ground state, and one finds that this is actually giving by that, and when you want to send gamma to 0, it's diverging, and you get like this is expected, since it's like XXX. And when one wants to refine this procedure, one has to take into account this should be an integer number, and then one can actually predict when one is at some finite lattice L, in which region of the anisotropy one gets the ground state as So when one has also like the densities, one can also compute other quantities like the energy density, the thermal velocity, the surface contribution. I'll spare you the details since they are not really important, since they just go into the CFT analysis as like some constants here. So when one looks at like these formula from CFT, which is relating like the boundary CFT to the lattice model, like Cardi did, yeah. One can then study like the scaling behavior of the energy states, and then can extract here the central charters of CFT, the primary scaling dimensions, and the level of descendants. So when you do that analytically, you obtain this object here for the effective scaling dimension, and this is all fine here, but the very, very important part is that you get like a contribution here, which involves like the difference of the Bethe roots, or the difference of the number of the Bethe roots of both lines. This is actually this Z here, which is actually a combination of the dressed charge matrix. This goes to infinity, and hence this term vanishes actually in the thermodynamic limit. So this is very interesting, since when one actually looks at the numerics, then one finds that it vanishes as, so this without the square vanishes as 1 over log L. So you have like logarithmic corrections, decreasing logarithmic corrections. And then the idea is actually to find a variable in the lattice which brings these logarithmic corrections under control. So then you identify a conserved quantity in the lattice which parametrizes these. And this is the quantity I've introduced before, the quasi momentum operator. Since when M1 actually calculates, you can also like solve the Bethe equations for various lattice sizes, then you can calculate the energy via that, and also like the quasi momentum. Then you find actually numerically that the scaling dimension can be parametrized via lattice quantities as this quantity, and this is what we have done numerics, and you find actually a perfect matching, right? So the black dots are the ones which are obtained by the formula by calculating the energies, and the red crosses are then the quantities which are obtained by the quasi momentum operator. And you find, perfect matching for various dn's and also various alpha and various gamma. You see perfect matching, and also like this decreasing thing which was also predicted. So this is nice, and then one wants to identify it with the CFT. So, and then I'm here importing some knowledge about the black hole CFT from Roland and Schomerus. So they are having this central charge and this primary conformal fields. And here, this is like the bit where the non-compact part goes in, since this has actually not just a discrete variable, but a continuous one. So when one then calculate from the CFT the effective scaling dimension you should observe in the lattice, you divide this by -24, and then adding this. So this is this, then this is this, and when you divide this by -24, you can complete with this thing the square here to obtain this quantity, and you have also like added like the number of descendants. So when we compare this with the spin chain, we find that the level of descendants is controlled by particle hole excitations. And when we match these terms, then we can identify the variables of the CFT with some quantities in the lattice. We find that the K level is given by pi over the anisotropy, that N, which is basically the momentum, and the winding number is 1, and that these continuous component is then given by the quasi momentum operator. So this is very, very nice. So when one has this, once is basically finished, and one can say that in the open case also like this region is described by the black hole CFT. However, let's come to the conclusion, some puzzles remain. Of course, one can now try to fill in other gaps of the space parameter space diagram. Also like the density of stage, which is basically needed to make like a various, so which would be then when you have there like a matching, it's like also even better. But however, to calculate these in the lattice, one needs to go to a very large lattice sizes, which we haven't done, and which is actually better to do via nonlinear integral equations. This was done in the periodic case, and there was a matching of the density of states observed. However, we haven't done that, so this was also like further directions, and I want to close with some points which we find like this. Due to the symmetry, the ground state, so we have spontaneous symmetry breaking the ground state, and we have like also the ferromagnetic XX model in the limit. This is also different to the periodic one, and the main point is like that the underlying CFT is still given by this black hole CFT. We find also like continuous component, and the main punchline is that this quasi momentum operator parameterizes the continuous part of the spectrum, which is what we also have done is we also like looked like at the discrete part, and then you find this is also parameterized by the quasi momentum operator. But I guess yes, my time is over, so I just want to thank you for your attention.
Thank you for the nice talk. So are there any questions?
Sorry, could I ask something? Maybe just could you go back to your phase diagram? Yeah, maybe that one already is fine. I mean, on the left, you have all different parameters alpha, but all correspond to the same ferromagnetic.
Yeah, it's just a normalization of, so that when you go back to the Hamiltonian.
But is there like a reason? I mean, because you're tuning different alpha, but it seems why it goes to the same model. Because for periodic case, I know that it does not go to the same model, right? If I tune different alpha, even at isotropic point. But here you have all the same model. Is there like a reason? Because on the line, on the green line, you see that it's actually different, because I mean, if you tune different the gamma, it's different model. But on the left, it all seems to me all the same model. Why is the case?
It's actually a good question. I mean, you can see it directly from the Hamiltonian, since then the alpha goes just in as a normalization constant. But maybe for a physical reason, I actually don't know a good physical reason for that.
Okay, thanks. No problem.
It's actually
okay,
a good
thanks.
question why you have like, I mean, here's like definitely different than
But also in the periodic case, we know that if you change different alpha, it corresponds to different models, right? I mean, okay. Anyway, thanks.
Maybe a related but more naive question is the theory in the limit in which alpha and gamma are both small somewhat simpler, and you can really see that small corner on the top bottom left?
This year?
Yeah.
I mean, as you go for slower, lower and lower gamma, it's harder. The numerics are more and more involved, since like the spin of the ground state is getting higher and higher and higher. But sorry, what was your...
But the theory doesn't simplify that you can neglect certain terms in the Hamiltonian? No.
No, I don't think so.
Okay.
Yeah.
Thank you. So may I just ask for the motivation? I mean, what do you want to study? What is the advantage of looking at open boundary conditions? If you're interested in the black hole field theory or in the lattice realization, you can take the periodic case as well. There's
so first of all...
So why are you studying this with open boundaries?
First of all, it's interesting, since we have observed like that you need to fine-tune the boundary conditions. So this is a very specific choice, that you have like this huge symmetry, right? And there was other works by Robertson of this group. They have studied this before, and to really observe the continuous component, it's actually yeah, quite hard, since he has, I mean, he has published 2 papers and he was not able to, when you have to fine tune this, and this is now then, yeah, for these certain boundary condition extending like the diagram, but we, I mean, just for, yeah, sake that you have like continuous, yeah, scaling dimensions. So this is just for the sake, but we don't want to go like, yeah, study the whole CFT. I mean, it would be interesting actually to study the effects of the open boundary conditions on the density of states, right? This would be a thing which one can then do. No. Yeah. Yeah, exactly. So you need to choose very specific boundary conditions.
So one specific choice is periodic and another specific choice is nuclear.
Yes, exactly.
And you have an idea of the class of all?
Sorry?
What is the class of all?
Yeah, this is interesting. No, I don't have any idea, but yeah, it's interesting. We have looked actually at diagonal ones, right? So this would be the first thing to increase. But there are certain problems occur that we get like logarithmic increasing scaling dimensions, so that they are basically then going out of the lower energy spectrum in the limit, and then basically the only stage which then survived are again these dn, so when the number of beta roots on the both lines coincide, right? But then you have no variable to basically, yeah, get lots of states, and then you have like, yeah, just a discrete scaling dimension. So when you go to open boundary diagonal conditions, there are also like some problems occurring. Yeah, so it's really due to like to identify a specific choice of boundary conditions which lead to yeah.
I have one small question. When you take gamma going to 0,
Yeah.
then the level k goes to infinity, so you have a kind of classical limit of the black hole. Can you?
Yeah. Okay. This is, yeah. I mean, this is interesting, but to be honest, I'm not that into the conformal field theory. But this would be interesting. Yeah, to study. But I'm fortunately I have no clue. No. Okay.
Thank you. So let's thank again.